Okay, we'll get started, right? So, I think we're going to start with we are going to look at oblique incidence on dielectric interfaces for this class. Okay. And I am going to divide the page into two columns. For two different configurations. Okay. So, I will start with the first configuration. Okay. So, similar to the last lecture where we talked about normal incidence. Okay. So, we have an axis which was the x axis here, z axis here, and to form a right handed triad we had a y axis marked in this way. We talked about a specific case where the polarization of the incident wave was having electric field component in the plane of the diagram, magnetic field was perpendicular to the plane of the diagram, and the transmitted wave, the assumption was that there is no change in any polarization, and then we calculated what is the value of reflection and transmission coefficients, and we found that it looked exactly same as what we got in transmission lines, except that in transmission lines we did not calculate transmission coefficient, we calculated only the reflection coefficient, right. Nevertheless, the key thing that we saw in the previous lecture also was that the boundary conditions for the case of dielectric interfaces is that the tangential E field and the tangential H fields are continuous. Please remember that this is valid only for dielectric interfaces. For dielectric metal interfaces, we will have a separate lecture where we will derive the reflection and the transmission coefficients, but the boundary conditions are slightly different because it will involve surface currents. Okay. So, we derived the gamma which looks like eta 2 minus eta 1 by eta 2 plus eta 1. You can assume this eta 2 to be load in the case of transmission line and say that it is ZL, okay, characteristic impedance, and eta 1 could be Z naught characteristic impedance of the first transmission line, and then you will get ZL minus Z naught by ZL plus Z naught. This is what we had seen, plus we also calculated another new quantity called tau, alright. The tau was the transmission coefficient and it had the form 2 eta 2 divided by eta 2 plus eta 1. This is some quantity that we had not calculated before, alright, and there was a relationship between the transmission and reflection coefficients. Okay, and we found that 1 plus gamma is equal to tau, alright. This means that the transmission coefficient can be greater than 1 when we are talking about the value of electric field, alright. So, it means that your incident electric field can be 1 volt per meter. The transmitted electric field can always be higher than that, but it does not mean that the energy conservation is violated. Whenever electric field goes up in the second medium, the magnetic field will proportionally go down to make sure that the conservation of power or conservation of energy is held correctly in the system. This is what we had seen broadly, and in today's lecture we will create a slightly more complicated system where the wave is going to hit the interface at an angle with respect to the discontinuity of the plane of incidence, and this kind of setup is not there in transmission lines. Okay, so, this is a difference. Okay. So, I am going to mark the axis in the exact same way as we did before. So, I am going to have the x axis marked vertically. This is my x axis, okay. The z axis is what we were taking on the horizontal, okay. And to form the right handed triad, you will need to have your y axis going out of the paper. It is the same coordinate system as what we had used in the last class. Okay. Now, there are some small definitions that we will need to look at. Okay. First of all, the term that we will call as plane of incidence. Okay, it's a very important term, plane of incidence. Okay. So, before defining this, I will define a couple of things much more clearly. Okay. So, I am having a medium, all right. On the left hand side, the dielectric constant is epsilon 1. On the right side, the dielectric constant is epsilon 2. So, it is a dielectric interface, and I am also assuming that mu 1 could be equal to mu 2 like in majority of the cases. Okay. Even if it is different, does not matter, but there is no sigma coming into the picture, sigma is 0 in both the sides. Okay. So, epsilon 1 and epsilon 2. The interface between epsilon 1 and epsilon 2 is at z equal to 0. So, this point here corresponds to z equal to 0, all right. So, z less than 0 corresponds to one dielectric with dielectric constant epsilon 1. Z greater than 0 corresponds to another dielectric with epsilon 2, and we are assuming that these two media are semi infinite, which means that on the left hand side this medium is extending infinitely, and on the right hand side this medium is also extending infinitely. The reason for doing that is we want to avoid more interfaces coming into the picture. Suppose you had another material coming in, then you would have one more interface and there would be a reflected wave from there and all that. So, right now we are taking a very simple case where there is two semi infinite dielectric media on the left and the right. Okay. So, the plane of incidence in this case is going to be xz plane. So, whenever people talk about plane of incidence, okay, you have to draw this diagram with the dielectric discontinuity, okay, and you also need to mark some incident, reflected, transmitted waves, etc. So, I will go ahead and draw an incident ray. Okay. So, the incident ray goes and hits the interface at the origin. Okay. It can get reflected, part of it can get transmitted, etc. So, that means that you are going to be having some reflected ray going out like this, right, and you are going to have a transmitted ray, let us say going like this. Okay. So, in this configuration the plane of incidence is xz, okay, and z has the discontinuity in the dielectric permittivity. Okay. So, now having drawn these rays, there are many configurations possible simply because our E and H fields are actually vectors, right, they are vector fields. So, directionality can come into the picture. Okay. Now, the arrows that are marked here correspond to the direction of the k vector or the direction of propagation, more specifically it is the direction of your pointing vector, all right. So, in order to satisfy these pointing vector, it is quite possible that you can have multiple configurations of E and H. We have already seen that in the case of plane wave, you can orient your thumb towards the direction of propagation, but you are free to rotate the other two fingers, all right, about the wrist, and still you will be able to satisfy the condition of direction of propagation, but the E field H field configurations can be, rotating about this transversal plane. So, we need to put some guidelines and we need to talk about in more details. Okay. So, one of the configurations that I am going to draw on the left hand side, okay, is such that the electric field is out of plane, it is pointing out of the paper. Okay. This is one configuration, all right. So, now I can orient my thumb and I can position my electric field to be going out of the paper, and I get the direction of the magnetic field to be pointing downwards in the plane of the diagram. So, I can now mark the direction of the magnetic field as H. To be clearer, I will use some suffix. I will say that this is my incident electric field, this is my incident magnetic field. Please make a note that electric field is pointing out of the plane of incidence. Okay. In other words, the electric field here is perpendicular to the plane of incidence. Okay. E field here has only y component, okay. It is perpendicular to the plane of incidence and such a configuration we call this as perpendicular polarization. Okay. So, given a problem you should be able to identify the plane of incidence, then you should be able to draw an incident wave and clearly indicate what polarization you are considering. So, in this case the electric field is pointing out of this plane of incidence diagram that you have drawn. So, it is perpendicular. So, you can call it as perpendicular polarization. Okay. Now, this forms a right handed triad and the wave is going and hitting the interface. Since we are talking about oblique incidence, we can start marking some angles. Okay. Now, we have to mark what is known as the angle of incidence. Okay. The angle of incidence is the angle made by the wave with respect to the normal drawn to the interface. So, the normal here to the interface is the z axis itself, all right. So, we have to mark some angle and we will say that this angle is theta incident or theta I. Okay. Now, because epsilon 1 and epsilon 2 are different, you are going to be having intrinsic impedance mismatch at this boundary. So, that means that your wave is going to get reflected and part of it is going to be transmitted. So, let us start marking the red part which is the reflected ray. Now, we have to make some assumptions, all right. Now, we will say that in this left hand side we are going to be sure that the electric field is always going to remain perpendicular to the plane of incidence, right. So, we are making an assumption that there is no polarization change, all right, with respect to the directionality of the E field. So, there is no, suppose we say that the E field is going to be pointing out of the plane of incidence, right. The magnetic field will adjust itself to compensate for the direction of propagation, right. So, if that is the case, all right, we can go ahead and say that my reflected electric field is going to have the same characteristics of the incident electric field in terms of direction, all right. But now the k vector is going in another direction. So, in order to satisfy that, we are saying that the magnetic field is going to be aligning itself to form a right handed triad. So, since the direction is reversed over here, the magnetic field has to flip its direction compared to the incident. So, we can go ahead and mark a reflected magnetic field looking like that, right. Okay. Now, there is another quantity that we need to still mark, the angle of reflection, all right. I think many of us already know that the angle of incidence is going to be equal to the angle of reflection. So, you could mark it directly as theta I, okay. Theta I is equal to theta reflected. So, we just use one variable to denote the angle of reflection, okay. Now, proceeding to the transmitted part, okay. The transmitted part, again we are making sure that the E field always is is perpendicular to the plane of incidence. So, I am going to have E transmitted pointing out of the paper. Magnetic field is simply going to follow a similar form as your incident field. So, that means it is going to look like this to form the right handed triad. Okay. Okay. Now, there is one more quantity we need to mark here, which is theta t, and theta t can be different than theta I. Okay. So, we do know that there is something known as Snell's law, where n1 sin theta I is n2 sin theta t. So, it is quite possible that theta t is different from theta I. So, if epsilon 2 is different from epsilon 1, theta t will be different than theta I. And to just indicate that, I have marked a green color with a smaller angle. It could also be a different angle, right, depending upon the ratio of permittivities, etc. We will get to that later. Right. So, this is one configuration, and in this configuration we refer to this system as oblique incidence on a dielectric interface, but specifically we are talking about perpendicular polarization. That means the E field is always, for the transmitted reflected incident, it is always perpendicular to the plane. Under this scenario, we wish to calculate what is the value of the reflection and the transmission coefficient. Okay. So, that is the objective of the lecture for this configuration. Now that we have drawn this configuration, let me draw the other configuration on the side, so that we can work out one part and then go to the other part and try to mimic the same thing again, right. So, I will go ahead and draw the axis again. Okay. So, I am having the x z axis and I am going to be marking an incident ray. Okay. In this case, what we are doing is the magnetic field, okay, is going to be out of plane, okay, out of plane of incidence. Okay. So, the plane of incidence is x z. So, I am going to make a mark here and I am going to call this as h I. The direction of the arrow that is going to the interface is the direction of k. So, you can use your right hand, alright, and try to figure out what direction your E field will be. So, E field in this case is pointing up, right. So, I am going to be marking an arrow and say that this is my EI. Okay. The angle, is there an issue, error? Alright, there is an error, you immediately point it out, okay, before it gets big. So, it is theta I is the angle of incidence again, alright. Now, again we can have a reflected and a transmitted wave. So, I will also mark epsilon 1, epsilon 2, okay. I am having the ray going out like this, and the assumption we are making is the magnetic field does not flip its direction at all. So, what happens is you mark the magnetic field in the exact same way. So, this is going to be your HR. If this is your HR, the direction of the thumb will point to the direction of propagation and your magnetic field is going to look outwards. So, that means that your electric field is going to flip its direction. So, now it is going to point something like this. Okay. Once again we mark the angle of reflection to be the same as the angle of incidence, and then we mark a transmitted ray also. Once again the assumption is that the magnetic field remains out of plane and is not flipped, etc. So, we just mark this to be H transmitted. And in order to form the right handed triad with the k vector pointing in this direction, the E field will look like. Okay. So, just to be clear over here, so sometimes it can become difficult to remember this. E field perpendicular is perpendicular incident, E field in the plane is parallel, okay, because if you say H field perpendicular, you may be remembering perpendicular for both the cases. So, it is easier to remember in terms of electric field, because we defined polarization as dependent on electric field and how with respect to time the electric field direction is changing. So, this particular case is known as parallel polarization. Okay. There are also other notations that are used widely, for example, S and P polarizations, TE and TM polarizations, etc. but I think I will just stick to perpendicular and parallel because it is easy for me to remember. S and P is from some other language, I do not remember what S and P usually means, right. TE and TM one can say because the transverse part of your electric, transverse electric field or transverse magnetic field, etc. That is also one way of remembering. So, you can pick one of them, but I am going to stick to perpendicular and parallel for this set. Yeah. Okay. Now, once having created these two systems, then we have to start doing a few things. The first thing that we want to write down is expressions for incident, reflected and transmitted waves in both these configurations. Okay. So, we start with the case on the left hand side. So, I am having I am having an incident wave and I am going to write down some expressions. Specifically, I want to write down the expression for the electric and the magnetic fields. Okay. So, I will write down what we had seen before and then build on it. Okay. Okay. So, I am denoting the electric field incident to be EI. It does have some magnitude and a direction, all right, and it varies with respect to the space, right, as minus j k I dot r. We had seen that for a plane wave that is traveling in an arbitrary direction, the way to write down the expression for the electric field is EI naught exponential minus j k dot r, where r is your position vector, it will be x x hat plus y y hat plus z z hat, k I is supposed to be found by us. Okay. So, we will do all of these now systematically, but you need to remember that this is the generic expression for the electric field. Now, our objective is to calculate correctly the value of k I dot r, plug it into this expression and then start to look at what we can do with it. Okay. So, from one of the previous lectures, we will remember that k I in arbitrary direction will have components in x, y and z axis. Okay. So, in order to find the dot product between k and r, you need to know kx, ky, kz, then only you can find out the dot product, right. We also saw that the ki is actually beta n hat. Okay. In the earlier lectures, we had said that it is multiplied by the it is the combination of the phase constant pointing in the direction of the unit vector along k, right. So, if you go back a couple of lectures, okay, so we had written the expression k to be equal to beta times n hat, where n hat is the unit vector in the direction of travel. So, beta is the phase constant, it is simply 2 pi by lambda. So, now we know we can estimate 2 pi by lambda provided lambda is given to us in the problem, alright, it is a constant that can be evaluated, you need to get some input in the problem, which means that now I have to find out what my n hat or the unit vector is going to be, alright, in order to find out the expression for the plane wave system that I am doing. Right. So, I can always say that beta, alright, for the medium on the left hand side is beta suffix 1 or beta 1, alright, to be very clear, because permittivity is epsilon 1 and we already know that the phase constant is going to be different in different media, alright, the velocity is also going to be different in different media. These are two things that we have seen from simulations in the past, okay. Which means that now the problem is really how I correctly ascertain what my nx, ny, nz components are going to be. These are the components of the unit vector, okay. Okay. So, now I go back to my diagram and the direction of travel is given by the arrow on this blue color ray over here. This is the direction of the unit vector n hat, all right, and its magnitude is going to be equal to 1 because it is a unit vector in that direction. So, I can take that unit vector, I can decompose it into having an x component and a x component and a z component. Sorry, because we have drawn a weird axis, all right. X component usually we mark it along the horizontal, but we have drawn x to be in the perpendicular direction. So, all we have to do is the unit vector has to be resolved into a x component and a z component. Now, I can see clearly that I can decompose this vector, okay, by drawing a vector in this direction and a vector in this direction. That means, I am having positive z axis and positive x axis, all right. So, if I go along the positive z and along the positive x, if I draw two vectors, I can decompose my unit vector in that direction, right. So, now I have to find this vector horizontal and this perpendicular. So, I can use some identities for angles. So, this angle that we have marked is theta I. So, in this triangle, using the alternate internal angles are supposed to be equal. So, I can mark the angle on the left hand side here to be also theta I. Okay. Now, I can write down, right, sine and cos theta I. Nx, which is the vertical component, divided by n is equal to sine theta I, right. So, we will just write down the components of n. Okay. So, I am having sine theta I to be the x component, okay. Ny, there is no component in that direction, all right. So, I can just mark it as 0. And the z component, if you look at the triangle, all right, it is along the horizontal direction. So, it is cos theta I. The other way you can also think of is, you can always write cos theta I, all right, is equal to nx divided by n, n is equal to 1. So, cos theta sin theta I is equal to nx, or you can always write cos theta I is equal to nz divided by n hat, or cos theta I is equal to nz hat. So, the components you can find out by using elementary trigonometry. Once you have found that, then it is very simple. We can always write down what k I is going to be like, right. So, we know that it is going to be beta of the first medium multiplied with some n hat, okay. So, n hat has 3 components. Let us just write down these 3 components. So, sin theta I x hat plus 0 y hat plus cos theta I z hat. This is how you will decompose your unit normal vector, or a unit vector along the direction of k, right. Or simply put, you can say that this is beta 1 sin theta I x hat plus beta 1 cos theta I z hat, okay. Now, what we can do is, we can denote the position vector to be any point x denoted by x in the unit direction x hat plus y, the unit direction y hat, plus z, the z unit vector direction z hat. So, it has the coordinates of x, y and z, right. X, y and z could be anything, right. It is just a position vector. We need to find the dot product of k I and r, okay. So, now I can directly write down the electric field expression is equal to E I naught exponential minus j, it was k dot r, right. So, I am going to take beta 1 x sin theta I, okay. So, I am multiplying these two and then z cos okay. So, I have written ki, I have written r, I have taken a dot product, that means I have multiplied the x components together, z components together, y components we have ignored because one of them is 0, right. So, this would be the expression for the electric field of the incident wave. So, given a configuration, now you should be able to systematically do this and write down the expression for a plane wave electric field going in an arbitrary direction towards the interface. That part it should be clear by now as to how you have to do it, right. Now, in order to do this a little bit further, now that we have the expression for the incident wave, why don't we try and write down the expression for the transmitted and reflected wave. So, we will start with reflected. Okay. Now, your reflected wave can be written as say some ER, and it has some magnitude ER naught, direction, right, and then you are having some e to the minus j kr dot, again r is a position vector, it is just xx hat plus yy hat plus zz hat. Okay. So, now our objective is to just find out kr and then find out the dot product. Okay. Once again, what we can do is we can say that kr is simply phase constant beta multiplied with some n hat, where n hat is the unit vector in the direction of travel of the reflected wave. So, it is going like this, the configuration, okay. Which means that effectively I have to figure out the components of n hat, nx, ny and nz. Okay. Right. So, nx, right. So, I go back to the diagram. Okay. So, I am having this going like this. So, I can say that the arrow is pointing in this direction. I can write this to be a combination of a vector going like this plus a vector added like this, right. Right. The summation of the vector going left and up will give me n hat in the direction of travel, right. So, this means that in the z axis I am looking at going towards negative z direction, but in the x axis I am still looking at going in the positive x direction. Once again I can use trigonometry, I can mark the angle to be equal to theta I here, this is theta I, same configuration here. So, that is also theta I. I can write down what is the value of sine and cosine of theta I, I can write down what is nx and nz. Okay. So, in this case nx will look like sine theta I. So, I will write down the components of okay. So, I will have sine theta I, y component is 0. The z component however is going in the other direction. So, you have to account for that and you have to write that as minus cos theta I. Okay. Once you have written the components, you can write down what the kr is going to be. So, you can write it is kr is going to be beta multiplied by sin theta I x hat, okay, minus cos theta I z hat. Okay. Once you have found this, the next step is very trivial now. All you need to do is write down the form for the position vector. Position vector that we are using is simply x x hat plus y y hat plus z z hat, and now I can write down the expression for my reflected electric field, right. So, I can write down ER has some magnitude and a direction, right, and with respect to space it is varying as e to the minus j beta 1, all right. So, it is in the same medium, right, k dot r. Okay. So, k dot r here is x sin theta minus z cos theta. Okay, x sin theta I minus z cos theta I. So, this is how you would write the expression for the plane waves. Okay. This part now should be very clear. Okay. Now that we are experts with this part, we can write down what is going to be the form for electric field for the transmitted. Transmitted field, let us say that I call as E suffix t. It is going to look like some E t naught exponential minus j k t dot r. You have to find out k t and then you have to dot it with the position vector x x hat plus y y hat plus z z hat, all right. Now, k t is going to have similar form as k I, all right. The only change is when you try to find out the components of n, instead of using sin theta I cos theta I, you will be using sin theta t cos theta t, that is all right. So, I will directly go ahead and write down the expression, right. Another thing that we have to notice is the phase constant for the second medium is beta 2. So, it looks like x sin theta t plus z cos theta t. Okay. Now that we have written the electric field expressions for the incident wave, reflected and the transmitted wave, all right. What we can do is we can make our life a little bit simpler by just saying that look, the incident magnetic field is going to follow Ohm's law. Magnitude of it is going to be equal to the magnitude of electric field divided by the intrinsic impedance of medium number 1. Right. So, I can simply say that this is going to be divided by eta. That gives me the magnitude directly, all right. I know that it is oriented along y direction, okay. Wait, which configuration are we seeing? Oh, it is in the xz plane, sorry, okay. HR is simply ER divided by eta. And just to be specific, I will just mark this as eta 1 for these two cases, because they are in the same medium. Okay. If you wanted to write down the detailed magnetic field expressions, the procedure is going to be exactly same as what you did for the electric fields. Okay. You can resolve the components of the map. The only thing is you will have to be careful with the components, which component is going along the x direction, which component is along the z direction, etc. And you will have to be a little careful with your k vector, that is it. Right. But the procedure is exactly the same, there is no big difference here. Now, once we have written these two expressions, for example, we have written electric field expressions for the incident, reflected, transmitted wave in detail. Magnetic fields, we have just said that using Ohm's law, magnetic field is going to be equal to electric field divided by characteristic impedance. That is what we have done so far, right. Now, what are we interested in? We are interested in finding out the reflection coefficient and the transmission coefficients in this configuration, right. So, all we need to do now is we need to look at the boundary or the interface. So, here the interface is at conveniently z equal to 0. Okay, the position coordinate with respect to z, when z equal to 0 marks the discontinuity between medium number 1 and medium number 2. So, at z equal to 0 is the exact interface, alright. So, at the interface we need to apply boundary conditions, and the boundary conditions for dielectric interfaces is tangential E fields are continuous, tangential H fields are also continuous, that is it, alright. So, now what we are going to do is we are going to apply these boundary conditions. Okay. So, all we can say is the way we have drawn the configuration here, the electric field is perpendicular to the plane of incidence, which means that all the electric field is tangential to the interface. Okay. So, the interface is like this and your electric field is like this. So, it is all tangential. So, you can simply write down that EI plus ER in medium number 1 is going to be equal to ET in medium number 2. Okay. Okay. This is simply because EI and ER are assumed to not be flipped in directions. So, EI is pointing one way, ER is also pointing in the same way. So, we have added EI with ER and it has to be equal to whatever is being transmitted ET. So, this is actually should give you some idea as to transmission coefficient could be greater than transmission coefficient could be greater than 1, and the transmitted electric field on the right hand side could be greater than incident electric field, right. So, it is not a very unnatural consequence. We still have to remember that magnetic field will adjust itself if this happens. So, this is one boundary condition, okay. And for the magnetic field we have to take the tangential components and then we have to see that it is continuous. So, we have to go back to the diagram. Okay. Now, our HI is looking like this. For the sake of some clarity, what I will do is I will mark another HI here, right, and I need to take the tangential component. So, it is pointing like this. Okay. So, it is pointing like this. I need to find this component and then I have to mark it for all the 3 rays at the boundary, and I have to apply tangential field is continuous, right. So, I can use trigonometry to find out the angles, okay. I can use trigonometry to find out the angles. I will not go into too much detail, but I will just write down it will look like HI cos theta I. Now, remember that for the magnetic field the direction was flipped for the reflected case, alright. So, you have to be careful, you are having one vector going like in one direction, another vector in the other direction. So, you have to make HR cos theta I again is equal to HT cos theta T. All right, and this is at z equal to 0. So, you can also be more specific, saying that at z equal to 0. This means that whatever you wrote within your exponential minus j k dot r, all right, it is at z equal to 0. Okay. So, this just means that you are having EI naught plus ER naught is equal to ET naught. And for the case of the magnetic field, you can always write this down using Ohm's law. EI naught divided by eta 1 minus ER naught divided by eta 1 again, the same medium, is equal to ET naught divided by eta 2. All right. So, now we have some equations. We have equation number 1, equation number 2. Now, we have to say what is known, what is unknown, etc., and what we wish to solve for. Let us say that eta 1 and eta 2 are known. That is, you are given some value of permittivity, permeability for medium number 1, permittivity and permeability of medium number 2. You will be able to find out the characteristic impedance, all right, for medium number 1 and medium number 2. So, eta 1 and eta 2 are known. Okay. EI naught, ER naught, ET naught, etc. All right. Let us say that we want to find out the ratio of ER naught to EI naught, ET naught to EI naught. So, there are actually EI naught, if you consider it as unknown, ER naught as unknown, ET naught as unknown, then there are 3 unknowns and we have only 2 equations, right. So, we cannot solve. So, we take the ratio of ER naught to EI naught, ET naught to EI naught, all right. Oops, cos theta I, both the cases. So, this will be cos theta t on the right side. Okay. So, again theta I is given, theta t is something that you can calculate from Snell's law, because you have been given epsilon 1, epsilon 2, mu 1 and mu 2, right. Then you can calculate n1 sin theta I is equal to n2 sin theta t, then you should be able to calculate theta t. These are known quantities. We wish to find out what is ER naught by EI naught and ET naught by EI naught, right. So, in other words, you can solve these 2 equations, simultaneous equations, and you can write down gamma, which is nothing but ER naught divided by EI naught. Okay. The solution looks like eta 2 cos theta I minus eta 1 cos theta t divided by eta 2 cos theta I plus eta 1 cos theta t. It is a big formula and it is a very confusing formula. You will not be expected to remember this for your quizzes, etc. All right. If needed, all these formula can be given, or you could make a formula sheet, we will work it out, but you do not need to memorize. Okay. To just make a additional point, that this gamma and tau that we had previously written before did not have the polarization marked. All right. From now on, we have to be very clear. When we are talking about gamma, we have to say which gamma. Is it parallel polarization or perpendicular polarization, etc., has to become clear. So, we are talking about gamma suffix a perpendicular symbol to clearly indicate that this we have calculated only for a specific E field H field configuration. Okay. Now, once you have calculated this, you can also go ahead and try to calculate what the transmission coefficient tau will look like, and that is your ET naught divided by EI naught, and from the 2 equations that is going to look like 2 eta 2 cos theta I divided by eta 2 cos theta I plus eta 1 cos theta t. It is also possible that you are able to find out some relationship between gamma and tau. Okay. You can already see that the denominators are identical, all right, and it will look like 1 plus gamma perpendicular is equal to tau perpendicular. So, there is no issues with that. Okay. It looks similar as the case with the normal instance, where 1 plus gamma was equal to tau for similar polarization configuration. Okay. So, given a problem like this, you should be able to estimate the gamma, tau, and also say, for example, if an incident wave electric field is given, you should be able to figure out what the reflected electric field and the transmitted electric field are going to be like. Okay. Specifically, you should be able to tell what is the value of the electric field that is transmitted, reflected, given a configuration with incident electric field. Okay. Okay. Now, we can always go back and start filling the right hand side for each of these, right, and we will do it in the next class, and then we will start comparing the left and the right hand sides, all right, and we will also see some conditions. If you look at the gamma perpendicular condition over here, the numerator has a negative sign, already it should trigger some thought that is it possible for the numerator to be equal to 0. Okay, what would that be? All right, is it possible for the numerator to be positive? Is it possible for the numerator to be negative? All right, when these things would happen, what material configuration do you need? What is the relationship between epsilon 1 and epsilon 2 that will give you these things? All right, so we have to see when gamma will be 0, gamma will be negative, gamma will be positive. All right, and the same thing we have to do for the other polarization case also, and then we will try to see what condition corresponds to what, and we will give unique names to each of these conditions. All right, some of these conditions could be, you can say total reflection, or you can say Brewster's angle, something like that. All right, so we are going to assign different cases for these different conditions. So right now we have just done it for perpendicular polarization. In the next class, in a little swift manner, we will write this for the parallel polarization, now that you are aware of how to do this. Okay, and then we will try to draw inferences from what can happen when a plane wave strikes the interface, assuming that the E field or the H field do not flip, right, only one of them flips and the other one remains constant. Okay, and then we will try to make some inferences from them. Okay, I will stop.